All right, this lesson is on chemical equations. This is not so much on balancing, but actually on the types of reactions that you can expect in Chemistry 140 or just any chemistry class. Um, this is in reference to pages 138 and 139 in McGraw-Hill's General Organic and Biological Chemistry textbook. So when we look at an equation, let me just think about, let's say we have this substance. I can get it to, let's get a pen going. Say I have HCl aqueous, AQ. That's not the best AQ. Maybe we better try that again. HCl aqueous, AQ. All right, that's an acid. That's hydrochloric acid. Again, this is called hydrochloric acid. This is something coming up in another chapter, so you might as well think about it. Anytime you have a terminal hydrogen on the end with a non-metal like chlorine, and it's aqueous, which means dissolved in water, that's a good indication that we're looking at an acid. This is called a binary acid because it's only two components. And you say hydro for the first part and chloric for the second part. So this is hydrochloric acid. Let's say we're going to react that with a base. Bases tend to be metal hydroxides. So in this case we have sodium hydroxide. And again, this is aqueous dissolved in water. All right, so the question is, what kind of reaction do we have? So we have double arrows like this, which means it can be in equilibrium. So what reacts with what here? Well, if we look at this, if we would break this down into what's actually in the water, we would have hydrogen ions, and we would this would break apart into chloride ions, like so. And again, these would be aqueous. And the sodium hydroxide would dissociate into its ions, which would be the sodium ion. And that's a key term. Dissociate means that these are normally present in ions, and when it adds to water, it just breaks apart. Ions are not being formed; they were already present in the compound itself. So it dissociates. And then some of you argue, well, hydrochloric acid doesn't really dissociate. It's a covalent compound, and really what happens is when hydrochloric acid reacts in water, it's HCl reacts with water, and then we form the ions, the hydronium ion plus the chloride ion. And that's fine. I mean, that's, I think, if you want to say this was a gas initially and you bubble it through water, liquid, and then you get aqueous, and aqueous here. And that's fine. I think that's more technically correct. But for what we're talking about here is just trying to identify the reaction, what type of reaction it is, and what the outcome's going to be. I think it's fine just to think of hydrochloric acid as hydrogen ions and chloride ions. All right, so you have these ions present, and I don't really care for red. Let's try a different color. I like blue better. All right, so we're looking at this, and you go, well, what would combine with what? I think this is really important. This is a crucial step here because this is what you know. Like charges repel each other. So the hydrogen ion is not going to react with the sodium ion. They're both positively charged. And the chloride ion is not going to react with the hydroxide ion because they're both negatively charged. So if new things are going to be formed, it's going to be the sodium reacting with the chlorine and the hydrogen reacting with the hydroxide ion. So let's put those together. We would get sodium chloride, also called table salt. Now this would be aqueous because it's dissolved in water. And you go, how do you know that dissolves in water? Well, it dissolves in water because of the solubility rules. So that may be something you want to look at. That's really going to be important here in determining what the products are going to be. Solubility, we know that all group 1A salts are group 1 salts. So this is sodium ions out of group 1. All salts made with group 1A metals are water soluble. So sodium chloride is water soluble. And then the other substance we get is the hydrogen ion reacting with the hydroxide ion of the base, and we get water. All right. So this we would write as, we can write it as a liquid, or we could write it as aqueous, either way. Okay. So what's really going on? Tell me what's really in the solution. Well, the sodium chloride, because it's water soluble, the sodium ion does not actually combine with the chloride. So what we actually have in a beaker, if we mix these things together, would be sodium ions and chloride ions. But the water really does stick together. The hydrogen ion and the hydroxide ion actually do stick together. And actually, I think more technically, I probably should just say this is aqueous. I've got another reason why I think that now. I've seen it written both ways, but starting to think a little bit more about a pure liquid does not go in the equilibrium expression, and we want that in the expression. That's something later on. It's not really required at this point. All right, so this is called an ionic equation. So ionic equations show you what's actually present in the solution. This equation up here, which was what we're used to seeing, is called the molecular equation. And the advantage of the molecular equation is it's easy to draw, it's compact, it's easy to balance. We could put a coefficient out, in front of these very easily and balance the equation. The ionic equation shows us what's really in solution. And then here's the crucial one that you'll need to be able to do, which is net ionic. The net ionic equation shows the driving force for the chemical reaction. It shows us what is actually changing chemically from the reactant side to the product side. So when we look at this reaction up here, you notice the chloride ion, it's not changing. It's the same on the reactant side as it is on the product side. Same thing with the sodium ion, not changing. So there's no chemical reaction really between the sodium and chloride. Nothing's changed. There's still ions in solution. But there is a change here. The hydrogen ion, which was dissolved in water, reacts with the hydroxide ion, which was dissolved in water. And we get for a product a new substance that has different chemical and physical properties than hydrogen ions or hydroxide ions, and that's water. All right, so that's the net ionic. When you remove what we call these ions that do not change from the reactant side to the product side, when we remove those ions from the equation, then we get the net ionic equation. And these ions that do not change from the reactant side to the product side, those are called spectator ions. Spectator. Yes, we have to have them. You can't go out and buy a bottle of hydrogen ions, because if you did, once you took the cap off, a big lightning bolt would come out. Same thing with hydroxide. You can't go out and buy a bottle of hydroxide ions. You have to buy an electrically neutral solution. And so with hydrochloric acid, it's hydrogen ions and chloride ions. With sodium hydroxide, it's sodium positive ions and hydroxide negative ions. But when it comes down to the chemical reaction, it's actually the hydrogen ions of the acid react with the hydroxide ions of the base to form water. This is sometimes called a neutralization reaction. So what is a neutralization reaction? When you have acid react with base, you form a salt and you form water. All right? This is also called a double displacement reaction. The chlorine and the hydroxide and the sodium and the hydrogen, they all swap partners here, up here in the ionic equation. And so this is also called a double replacement reaction. All right. So ways to classify: this is an acid-base reaction. It's a double replacement reaction. And the net ionic equation is the hydrogen ion of the acid reacts with the hydroxide ion of the base to form water. I hope that helps. All right. So let's go to another slide. And we'll try another one of these. All right, so here's another classic example. We take silver nitrate. All right, and this is aqueous. So this is silver nitrate, the solute, dissolved in water, so that's why we have the aqueous. And we're going to react that with, let's say, potassium chloride, which will also make aqueous. Again, which means dissolved in water. All right, so this is what you got to do. You have to evaluate, does silver nitrate dissolve in water? That's the first question. So according to the solubility rules, nitrate ions dissolve in water. And so what we actually have in water is silver ions plus nitrate ions. And so this would be aqueous, and this would be aqueous. All right. And then we got to evaluate the potassium chloride. Well, all group 1A salts or group 1 metal ion salts dissolve in water, so this is going to dissolve into potassium ions in water and chloride ions. All right, and again, AQ symbolizes that it dissolves. So what's going to react with what? Well, the only thing the sodium could react with is the chloride ion. Again, cannot react with potassium, like charges repel each other. And so if we react these, we would get silver is a positive 1 ion, chlorine is a negative 1 ion, so they would combine 1 to 1. Positive silver combines with the negative 1 chloride. Now, what you have to do is you have to evaluate this compound. Does it dissolve in water or not? So if you look at the solubility rules, this one does not dissolve in water. This ionic substance does not dissolve in water. So we put solid for the symbol here. So it's going to precipitate out. Maybe you've seen this in the lab where you took two clear solutions and you poured them together, and all of a sudden you get this milky white precipitate form. And so that's what this would look like. This would be a milky white precipitate called silver chloride. And then we have, so over here on the other side of our net ionic reaction, we would have silver chloride solid. And then we have to evaluate the other compound. Does potassium nitrate dissolve in water? Well, it does. All group 1A metal salts dissolve in water, so that's going to be a positive potassium ion and a nitrate ion. And these would be AQ and AQ. Aqueous. So up here we would write KCl, potassium chloride, aqueous. All right. So again, this is the molecular equation. Easy and compact to write. This is the ionic equation. Shows us what's actually present in the solution. And then the last equation is, where is the chemical change? What's actually changing chemical form from the reactant side to the product side? That's what the net ionic reaction shows. So, what type of reaction is this? Well, first of all, you should say, I know it's double replacement, or sometimes we just say DR for short. Double replacement. The silver, the potassium are swapping out with the nitrate and chloride ion. So all four things are changing to something else. So that's double replacement. The type of reaction this isn't an acid-base reaction. We never saw any hydroxide or hydrogen ion form in water. But what we did see is we saw the silver chloride precipitate out. So notice again chemically the nitrate ion does not change from the reactant side to the product side. All right. The potassium ion does not change from the reactant side to the product side. And so those are spectator ions, the nitrate ion and the potassium ion. So if we take the spectator ions out, we get silver positive ions, aqueous, react with chloride ions that are negative, and that's also dissolved in water, and that forms the precipitate silver chloride, and we would say solid here. So this is called a precipitation reaction. When you have when the reactants are aqueous and then a solid forms, that's called a precipitation reaction. All right. Let's look at another one. Let's do one for Kentucky. All right. All right. So in Kentucky, we mine calcium carbonate. Calcium carbonate. What's the formula for calcium carbonate? Let's try a different color. Let's try purple. All right, calcium carbonate. Ca for calcium, CO3, and it's a solid. In Kentucky, we call this limestone. Some people call it dolomite. And it's made from the skeletons of sea creatures many years ago. And that was compacted in the earth. And it's a nice white solid. And we use it for to make quicklime, to sweeten the soil. Used also to make concrete. So this is an important component of concrete. Now what we do is we mine the calcium carbonate, which is a solid, and then we heat it up, and that's what this delta stands for, heat. And when we heat this up, it becomes calcium oxide, also called quicklime, which is sometimes what you see people put on their soil to sweeten it up, especially in horse country here. We want to sweeten the soil, make a nice tender bluegrass for the horses to eat. And then the other substance that comes off is carbon dioxide gas. All right, so this is not an acid-base reaction. It is not a precipitation reaction. Even though we have a solid here, solid's not on the product side. Oops, I made a mistake here. I just saw it. I wonder what I was thinking when I did that. Let me erase that. This is a solid as well. It's not aqueous. All right. It's quicklime. It's a solid. All right, so we get a solid and a gas as our product, so it's definitely not a precipitation reaction. This is a what we call a decomposition reaction. When you start with one substance and you end up with multiple substances on the product side, that's a good indication of a decomposition reaction. All right, start with one substance, end up with multiple substances on the other side. All right. Let's call that. This is not double replacement. This is decomposition. All right. Here's one that kind of bothers some people. You take something like copper bromide, copper 2 bromide. Remember, copper can come in at positive 1 form or a positive 2. How do you know this is positive 2 copper? Because bromine is a negative 1 ion and there's 2 of them, so that means that copper must have a 2 positive charge on it. So this is called copper 2 bromide, or if you're using the old system, it would be called cupric bromide. So we react that with zinc, which is also a solid. So this is a solid, this is a solid, and we heat this up, and the zinc replaces the copper, and we get zinc bromide plus copper metal released. So you're probably saying, why would I do something like this? Well, you're trying to purify copper. You want copper by itself. So you use the zinc over here to bond to the impurity bromine so that you get pure copper on this side. This is called, it's not a decomposition. We're not starting with one substance and ending with one. This is called a single replacement reaction. Single replacement. So the double replacement is a single replacement. All right. Charge on this is 0. Again, we wouldn't put these charges. Remember, when you draw your final equation, you don't show the charges, but just to kind of show what's going on. The zinc's 2 positive, this is 1 negative, and the copper now is 0. So copper went from a 2 positive ion to copper metal with no charge. So that's kind of interesting. So it's really an oxidation of the, or a reduction of the copper and an oxidation of the zinc. We'll talk about oxidation reduction reactions later on.